Good evening. This is our presentation on Chapter 5. In attendance, we have Ron Cooper, and in absence, we have Bethany Heap and Keith Giles. So this is a project that I'm going to try to implement to where we're going to upload our lectures onto YouTube so that this way it can be able to be accessible for students in proxy. So with all deliberation aside, let's begin with fundamentals of TCP/IP transport applications and security. So our objectives for this chapter are to view the TCP/IP Layer 4 protocols, which are TCP and UDP, and also some basic TCP/IP applications. I'd like to open up our lecture by speaking on some of the functions that the TCP transport layers provide. The TCP transport layer, its primary duties of the transport layer are to reliably and accurately transport and regulate the flow of information from a source to a destination. And end-to-end control and reliability are provided by sliding windows, sequencing numbers, and acknowledgments. To understand the reliability of flow control, think of someone who studies a foreign language for a year and then visits the country where that language is used. So in conversations, words must be repeated for reliability, so that people must also speak slowly so that the conversation is understood, which relates to flow control. The transport layer establishes a logical connection between two endpoints of a network. That process is called the handshake, where the initial sign and acknowledgement are passed. Protocols inside the transport layer segment and reassemble the data sent by upper layer applications into the same transport layer data stream. And this transport layer data stream provides end-to-end transport services. The two primary duties of the transport layer are to provide flow control and reliability. That transport layer defines end-to-end connectivity between host applications. The basic transport services are as follows. Segmentation of upper layer application data. So we're separating the payload in order to ensure that we are passing data reliably between 2 points. The establishment of end-to-end operations through the handshake. The transportation of segments from one end host to another. Flow control provided by sliding windows. Reliability is provided by sequence numbers and acknowledgments. TCP/IP is a combination of two individual protocols. IP operates at layer 3 of the OSI model, and it's a connectionless protocol that provides best effort delivery across a network. TCP operates in a transport layer and is connection-oriented service that provides flow control and reliability. When these protocols are combined, they provide a wider range of services. The combined protocols are the basis for the TCP/IP protocol suite. The internet is built upon this TCP/IP protocol suite. So I'd like to speak a little bit more about windowing. With windowing, it is a means where there will be a set limit of packets that will be passed after the handshake. So it's as if we establish the connection first, and once the connection is established, then that window is a set rule or set limit of the amount of packets that are passed between two endpoints. Once that limit is reached, the session layer and transport layer will assess to see if there are any errors. If there are any errors within the initial window of time, which is 3 packets, then we would pass that missed packet back across the data plane in order for us to be able to complete our project. So, for example, if we have a limit of 3 packets that are passed, packet 1 is received, packet 2 is not, packet 3 is received. Then at that point, we would go back and ensure that packet 2 is received once the session layer schedules the reissue of packet 2. Our next slide shows the anatomy of the TCP header field. So, although you do not need to memorize the names of the fields or their locations, the rest of the section refers to several fields, so the entire header is included here just as a base reference. The most important part of the TCP header field are the source port and destination port. So now we're looking at how just networking operates. It's either working on a source MAC address or destination MAC address, or source IP address or destination IP address. Now that we're operating in layer 4, we're looking at the source port number and destination port number. Now, another important portion is the sequence number and acknowledgement number. This would determine the windowing and that portion of time that it would take for us to send. So in other words, the sequence number will indicate what packet is being sent, and it will also indicate the expiration. The acknowledgement number will also indicate that the packet has been passed successfully. The window would indicate the limit. We have an urgent header, it's a binary condition of 1 that would determine whether or not we need to send a stat. The checksum operates the same way as a frame check sequence. Okay. Our next slide shows an example of Hannah sending packets to Jesse with 3 applications. So, Hannah is sending packets to Jesse with 3 applications via TCP to provide a lot of features to applications, but at the expense of requiring slightly more processing and overhead compared to UDP. However, TCP and UDP use a concept called multiplexing. Now, the overhead that TCP renders is the fact that they go through to ensure that the data has been received. So that increases overhead. Now, multiplexing by TCP and UDP involves the process of how a computer thinks when receiving data. The computer might be running many applications such as a web browser, an email client, and an internet voice over IP application like Skype. TCP and UDP multiplexing enables the receiving computer to know which application to give the data to. Some examples will help make the need for multiplexing obvious. The sample network on this slide consists of 2 PCs, which is Hannah and Jesse. Hannah uses an application that she wrote to send advertisements that appear on Jesse's screen. The application sends a new ad to Jesse every 10 seconds. Hannah sends a second application, which is a wire transfer application, to send to Jesse to receive some money. Finally, Hannah uses the web browser to access the web that runs on Jesse's PC. The ad application and wire transfer application are imaginary for this example, but the web application works just like it would in real life. The slide just shows the example of the network with Jesse running 3 applications. It's a UDP-based ad application, a TCP-based wire transfer application. We want to make sure the money is there, so that's why we want to choose a connection-oriented protocol. And a TCP web server application. Jesse needs to know which application to give the data to. But all 3 packets are from the same Ethernet and IP address. You might think that Jesse could look at whether the packet contains a UDP or TCP header, but as you see in the figure, the 2 applications, wire transfer and web, are using TCP because these are reliable sources. We're dealing with money and most of all line of sight onto the network. So multiplexing is going to take these specific port numbers, whether it be a UDP port number of X, a TCP number of Y, and a TCP number of Z. I really should say letters, but we'll go with it. And it filters out the traffic, so that way the receiving node would be able to delineate what data belongs to what service. So it can be able to isolate where the data is coming from the ad service. It can isolate where the data is coming from the wire transfer data, and where the data is coming from the web page data as well. Okay. Okay, so our second slide continues our scenario with Hannah and Jesse, where we are sending 3 applications using port numbers to multiplex. So in our previous slide, I kind of alluded to this point. So Hannah is sending packets to Jesse with three applications using port numbers to multiplex. TCP and UDP solve this problem by using a port number field in the TCP and UDP header respectively. Each of Hannah's TCP and UDP headers segments use a different destination port. So each of the segments in TCP and UDP have a different destination number, so that Jesse knows which application to give the data to. This slide shows an example. Multiplexing relies on a concept called the socket. And a socket consists of three things: the IP address, transport protocol, and a port number. So for a web server on Jesse, the socket would be 10.1.1.2 because that is the IP address, writing on a TCP protocol using port 80. Because by default, web servers use a well-known port 80, which is HTTP. When Hannah's web browser connects to the web server, Hannah uses a socket as well, possibly one like this, which is 10.1.1.1 using TCP port number 1030. Hannah just needs a port number that's unique on Hannah's device so that Hannah sees that port 1030 is available and uses it. Hosts usually allocate dynamic port numbers starting at 1024 because the port numbers below 1024 are reserved for well-known applications like Telnet and port 80, which is HTTP. Now, on the other side, Hannah and Jesse use three applications at the same time, hence three socket connections are open. Because a socket on a single computer should be unique, a connection between the two sockets should identify unique connections between two computers. This uniqueness means that you can use multiple applications at the same time, talking to applications running on the same or different computers. Multiplexing is based on sockets, ensuring that the data is delivered to the correct applications. So let's pick this apart for a minute. So, mainly what this is saying is that the sender is going to use a well-known port for well-known services. So, port 80, for example, is going to be used for your web server from the sender. But the web server or the receiver is going to see it different. Kind of mimics a crossover cable effect between two like devices. So when you see we see outgoing port 80 as we click send or click enter to go to our website. Our receiver is going to see a random port number, so we can be able to identify the sending and receiving point. Okay? Otherwise, there could be confusion. So, our next slide shows the dissection of the sockets. So it's going to show connections between them. As we see here on Hannah's side of the fence, Hannah is using port number 1025 for the add application. For the wire application, she's using 1028. For the web browser, she's using port 1030. But Jessie is receiving it from another perspective, because she sees the add application writing on port 800. Wire applications is writing on port 9876, while the web server is writing on port 80. Okay?
Now would that be because she might be in a different state?
Good question. Potentially, even if they were in the same room, and if they're receiving on the same node, it's best that they see the port number as something different, because what happens when we transmit on two like devices using a straight through cable? It would be a jam. It provides that same effect if two nodes are seeing the same service the same way. So we'd have to have a crossover effect with two disparate port numbers on the sender and receiver. Okay? Good question though. Connections between the sockets. So this slide shows the three socket connections between Hannah and Jessie. The port numbers are vital of the socket concept. Well-known port numbers are used by servers Other port numbers are used by clients. Applications that provide a service such as FTP, Telnet, and web servers open a socket using a well-known port and listen for connection requests. Because these requests from clients are required to include both the source and destination port numbers. The port numbers are used by the servers and must be well known. Therefore, the service uses a specific well-known port number. The well-known ports are listed at www.iana.org, assignments/service names port numbers/service names port numbers.txt. It is a universe of information. Now, we have a rundown of some basic ports here. Popular applications and their well-known port numbers. This slide just shows some of the well-known ports and their applications. So, from here, we have port number 20, which is TCP, which is a TCP protocol, It uses file transfer protocol data. So it's a data line for file transfer protocol. Now, well-known port number 21 is file transfer protocol control. So it controls how it sends the data through file transfer protocol. Well-known port numbers 22 and 23. 22 is secure shell, also rendered through TCP. Port 23 is the protocol we all know and love remotely. It's Telnet. Telnet has a huge Achilles heel for security, and that Achilles heel is the fact that there is no encryption that's rendered when a remote session is taking place. So we can see the data that is passed with the right type of sniffer. Wireshark or Ethereal can be able to show anything and everything on that network while Telnet is running. Port 25 is a well-known TCP service called Simple Mail Transfer Protocol. It is the outbound service to send mail. Port 53 can either run on TCP or UDP, which is DNS, which stands for Domain Name Service. DHCP is UDP ports 67 and 68. 69 is UDP port service TFTP. Port 80 is HTTP. Port 110 through TCP is POP3, which stands for Post Office Protocol version 3. This is how we receive our emails that are sent from SMTP. Port 161 is Simple Network Management Protocol, which is run through UDP. And then finally, one of the most critical protocols that's out there nowadays, especially with network security, is port 443, which is Secure Socket Layer. Okay, so I alluded to at the beginning of our lecture, I alluded to the fact that when they initiate a connection, when a server and a client initiates a connection, they do so through a process called a handshake. And a handshake is nothing more than an initial exchange of signs and acknowledgments, just seeing if the node is ready to receive information. So we see with our web browser using port 1027. Now, we are trying to get information from the web server at port 80. So we're going to send a sign out to the web server indicating that we need its service. The web server is going to send a signed ACK saying, hey, I am ready for your service. And the web server is then going to send an acknowledgement back indicating, okay, let's do this. Let's start. Because now we know that both nodes are ready to receive information. So the TCP connection establishment. The TCP connection establishment occurs before any of the other TCP features can begin their work. Connection establishment refers to the process of initializing sequence and acknowledgement fields and the agreeing on the port numbers used. This slide shows an example of a connection establishment flow. This three-way connection establishment flow is called a three-way handshake. You will hear that a lot in Mr. Graham's class. This must be complete before the data transfer can begin. The connection exists between two sockets. Although the TCP header has no socket field of the three parts of the socket, the IP addresses are implied based on the source and destination IP addresses in the IP header. TCP is implied because a TCP header is in use and as specified by the protocol field value in the IP header. Therefore, the only parts of the socket that need to be encoded in the TCP header are, the port numbers. TCP signals the connection establishment using two bits inside the flag fields of the TCP header. This is called the sign and acknowledgement flags. These bits have a particular interesting meaning. The sign means that we are going to synchronize the sequence numbers. What port numbers are we going to use so that way we can understand each other? Which is a necessary component of initialization for TCP. Once that transaction has taken place, then at that point, we are now passing data through ACK-FINs and acknowledgements and ACK-FINs and acknowledgements. So the TCP connection termination, this slide shows the TCP connection termination once everything is taken care of. I'm going to recant my initial statement, because this process actually shows how the transaction ends. So how the process starts is we're going to start with the sign. I'm just letting you know, Ron, that I'm going to be using port 1020 for your port 80.
Okay.
My transaction is going to be through HTTP. You're saying okay, gave me the sign ACK. Here's my information on port 1020. And did you receive it?
Yes.
Okay, here's more information on port 1020. Did you receive it?
Yes.
Okay, here's more information on port 1020. Did you receive it?
Yes.
Okay, awesome. My deed is done, so now I'm going to indicate that I've acknowledged that you've received it. So now I'm letting you know that I've also completed the task. So I'm sending my ACK-FIN. Did you receive that?
Yes.
Okay, so now you've received the ACK-FIN, and then now I'm acknowledging the receipt, and I'm closing the connection. So the TCP connection termination is done once both devices acknowledge the fact that they've received the information successfully. What happens when we have a dropped packet?
Should go back to say you didn't receive it, you have to resend it.
Exactly. Excellent. So when that occurs, and ACK-FINs actually occur through windowing, so there's a lot of moving parts that go on during TCP as well. So once we get to that third, we're going to put this on pause for a minute, just letting you know so that way we can recover any data. And then you nod your head as acknowledging, and that will serve as the ACK-FIN. I'm terminating the connection. And at that point, it's acknowledged that we did. I reach out to the session layer to reschedule a resend of a packet. And then at that point, we start with the handshake once again. Hey, I got that packet ready for you. You good?
Yes.
Okay, so now at that point, you've acknowledged that you're good. So, okay, I'm sending the first packet now.
Received.
Okay, we received it. Sign and ACK. Okay, you received the packet. Looks like our deed is done. So I'm going to terminate the connection. And then your nodding your head shows that you're acknowledging, which is the ACK-FIN. And at that point, I'm terminating the connection. So you see how now through the use of signs and acknowledgements that TCP is a connection-oriented protocol. So TCP connection termination, this slide shows TCP connection termination. This four-way termination sequence is straightforward and uses additional flags called FIN bits. The FIN is short for finished, as you might have guessed. One interesting note, before the device on the right sends the third TCP segment in the sequence, it notifies the application that the connection is coming down. It waits on an acknowledgement from the application before the third segment in the figure. Just in case the application takes some time to reply, the PC on the right sends the second flow in the figure, and acknowledging that the other PC wants to take down the connection. Otherwise, the PC on the left might resend the segment repeatedly. TCP establishes and terminates the connections between the two endpoints, whereas UDP does not. Many protocols operate under these same concepts, so the connection-oriented and connectionless protocols are used to refer to the general idea of each. More formally, these terms can be defined as follows. The connection-oriented protocol is a protocol that requires an exchange of messages before data transfer can begin, or that has a required pre-established correlation between the two endpoints. While a connectionless protocol is a protocol that does not require an exchange of messages and that doesn't require a pre-established correlation between the two endpoints. It just goes. So with all deliberation aside, we have a UDP header here. So most importantly, note that the header includes the source and destination port fields for the same purpose as TCP. However, UDP has only 8 bytes. In comparison to the 20-byte TCP header, UDP needs a shorter header than TCP because UDP has less work to do. Let's face it, the only thing UDP is going to be concerned about is where it's coming from and where it's going. Did it get there? Okay, we're going to put a checksum in there just to see if it didn't. Okay, just to let me know, because frankly, UDP runs so fast, it's going to send it again. The only thing he needs to know is whether or not it happened. And all of a sudden, it's being sent back just on the regular. It is a very fast and rapid protocol. It does not take as much time to verify as TCP does. So, UDP's greatest strength is voice over IP communications. So, we're going to look at a scenario where an IP packet is sent by a voice call. So, most modern enterprise TCP/IP networks support voice applications as well. So, most commonly, the network includes IP phones, which are telephones that connect to a TCP/IP network using an Ethernet or wireless LAN connection. The phones send the voice bits inside IP packets. Applications need to send data over a TCP/IP internetwork. However, they need more than the availability to move the data from one application on one device to another application on another device. That communication has different characteristics or qualities, and the networking world refers to these qualities as qualities of service. QoS in general defines the quality of the data transfer between the two applications and the network as a whole. QoS often breaks down these qualities into 4 competing characteristics. Bandwidth is the volume of bits per second needed for the application to work well. It may be biased with more volume in one direction or balanced. For example, the whole effect with the uphill and downhill with your ISP. If it's coming from your ISP, it's going to be downhill, and you're going to have more bandwidth than you would when you upload. Okay. Delay is the amount of time it takes for one packet to flow from sender to receiver. The jitter is a variation in the delay. I used to work for a call center, and when I took my calls over voice over IP networks, sometimes I would hear and as I would hear that during the call, that's an example of jitter. And then sometimes if it got too much, then there will be a loss of the call in itself. Okay. So a loss is a percentage of the packets discarded by the network before they reach their destination, which when using TCP requires a retransmission. In UDP, we're not concerned about the retransmission. We just want to get the data over to stat. Okay, so comparing the interactive and real-time application requirements. So this slide compares the quality of service requirements of 3 example applications. interactive web browsing, which requires only medium delay, medium jitter, and medium loss. So this is basically TCP altogether. Real-time video requires low delay, low jitter, and low loss because we want to make sure we have a strong pipe in order to push video and sound. So the table in your text, it can be used to review the comparison between the data applications versus voice and video, as opposed to as a set of random facts to memorize. Through experience, we may see this on the test. Okay, DNS resolution. DNS resolution is when we request a web page. This slide shows the DNS process is initiated by a web browser in addition to some other related information. From a basic perspective, the user enters a URL such as Cisco.com. And at that point, we start to resolve the Cisco.com name into the correct IP address, and it starts sending packets to the web server. The steps shown in this figure are as follows. In step 1, the user enters www.cisco.com/go/learning-network into the browser's address area. Step 2, the client sends a DNS request to the DNS server. The DNS server usually learns the DNS server's IP address. The client usually learns the DNS server's IP address via DHCP. Note that the DNS request uses a UDP header with a destination port of the DNS, well-known port 53. Reference 5-3 for your port numbers. In step 3, the DNS server sends a reply listing the IP address of 198.133.219.25 as Cisco.com's IP address. Note that the reply shows a destination IP address of 64.100.1.1. The client's IP address, which is the client's IP address, it also shows a UDP header with source port 53. The source port 53 is because the data is, sourced or sent by the DNS server. In step 4, the client begins the new process of establishing new TCP/IP connections to the web server. Note that the destination IP address is the just learned IP of the web server. The packet includes a TCP header because HTTP uses TCP. Also note that the destination TCP port is port 80, well-known port for HTTP. Finally, the sign bit is shown as a reminder that the TCP connection establishment process began with the TCP segment, showing the sign bit is turned into binary 1. And at this point in the process, the web server is almost finished setting up the TCP connection to the web server. The next section picks up the story at that point, examining how the web browser then gets the files that comprise the desired web page. So, we see even a lot more moving parts, because now what we start with? We started with, okay, what IP address is www.cisco.com? So we're going to send a very rapid means to try to find that information through port 53. We're sending out through port 53. We got the query back from the DNS server. Now we're going to wrap this up into port 80, because now that we know the IP address, we're going to start sending some requests in order to get this information. So we're going to flip from UDP mode and now go into connection-oriented mode in order to start accessing that website. Okay. Now, mind you, we're dissecting a very rapid service that happens as a matter of seconds, depending on your bandwidth. Okay. So the next step would now be provisioning the GET requests through HTTP. So multiple HTTP requests and responses. So after a web client or browser has created the TCP connection, creating the handshake, then the client can begin requesting the web page from the server. Most often, the protocol is used to transfer the web page is HTTP. The HTTP application layer protocol is defined in RFC 2616. It defines how files can be transferred between two computers. HTTP was specifically created for the purpose of transferring files between web servers and web clients. So HTTP defines several commands and responses, with the most often used being the HTTP GET request. So to get a file from the web server, the client sends a GET request to the server, listing the file name. If the server decides to send a file, the server sends an HTTP GET response with a return code of 200, meaning, okay, I'm getting it for you right away, along with its file contents. So web pages usually consist of multiple files called objects. Most web pages contain text in addition to several graphical images, animated advertisements, and possibly voice and video. Each of these components is stored on a different object or file on the web server. So to get them all, the web browser gets the first file. This file may and usually does include references to other URLs. So the browser then also requests to get the information from other objects. This slide shows the general idea with the browsing, getting the first file, and then getting two others. So in this case, after the web server gets the first file, one called go/ccna in the URL, the browser reads and interprets that file. Besides containing parts of the web page, the file refers to two other files, so that the browser issues two additional HTTP GET requests. Note that though it is not shown in the figure, all these commands flow over one or possibly more TCP connections between the client and the server. This means that TCP would provide error recovery, ensuring that the data was delivered. So the moral of the story is that depending on your means of getting the information, it can be very rapid or it can be very collated through the use of TCP. Everything is based on a system of signs and acknowledgments. So we get the GET requests and we get the GET requests and we get the GET acknowledgments, sign and act. And in order to even initialize the process, we have to get a handshake established first in order to agree upon the port numbers that each of the nodes are going to be using. So this is supporting what I said during the beginning of the mod when I speak about line of sight, to be able to understand that the services themselves are on the same page of music to pass data. Okay? So this is it for Chapter 5, Fundamentals of TCP IP Transport Applications and Security. Homework tonight is the do I know the answer already questions at the beginning of the chapter.